Okay, here we are evaluating limits analytically, calc students. And this time we're going to do it instead of with pictures so much, by hand. Here we go, properties of limits. Basically, for a lot of limits, we're just going to evaluate them by direct substitution. That is, we're going to assume that the limit as x goes to c of f of x equals f of c. This is generally the case for any well-behaved functions that we call continuous. Now, when they're not continuous, it'll be pretty clear from the graph or from when you do the calculations. This is also known as the plug and chug technique. Here's some basic limits. That is, if you take the limit of a constant, x going to c doesn't change at all, so you just get b. If you take the limit as x goes to c of x, that's just a straight line, the identity function, you get c. If you take the limit as x goes to c of x to the n, you'll just get c to the n power. So let's evaluate some of these basic limits here. What's the limit as x goes to 2 of 3? Well, it's just 3. The limit as x goes to negative 4 of x will just be negative 4. And the limit as x goes to 2 of x squared is just 2 squared, which is 4. Plug in and chug in here. And these ideas continue now as we see that you can distribute the idea of limits over sums and products and quotients as long as the thing underneath in the quotient is not equal to 0. But a constant multiplier just kind of comes out in front and becomes b times the limit. Now the limit of a polynomial. So this one we can just kind of use plug and chug on. The limit as x goes to 2 of 4x squared plus 3 is just going to be 4 times 2 squared plus 3. So you get 4 times 4 plus 3. 16 and 3 is 19. Now let's try a different limit here. Limits of polynomial and rational functions. Again, you have to be careful with the rational function that you just plug in the bottom, because if it makes the bottom equal to 0, we're going to have to look at that in a very different way. So limit of a rational function. Well, let's just try this as plug and chug. 1 squared plus 1 plus 2 over 1 plus 1. And we get 4 halves is 2. If it involves a radical, we can sneak inside that radical as well. And a composition of functions, figure out the innermost function first, and then take the limit and use that in the outermost function. So the limit as x goes to the square root of x squared plus 4 will be the square root of 2 squared plus 4, square root of 8, which is 2 root 2. Limit as x goes to 3 to the cube root, so that's a cube root of 2 times 3 squared minus 10. Cube root of 18 minus 10. Cube root of 8 is 2. Now, what happens when the function doesn't agree with, basically that we get a problem, we get division by 0. Let's take a look at this one. We saw this before, and we found the answer graphically. But as you can see with this function, x cubed minus 1 over x minus 1, it does not exist at 1. It's undefined. We'll have division by 0. So if you just try plug and chug, you get 1 cubed minus 1 over 1 minus 1. You get 0 over 0. We call this the indeterminate form. Because 0 divided by 0 is not defined, and you could set it equal to anything. 0 over 0 could equal 42, because 0 equals 42 times 0. Or 0 over 0 could equal pi, because 0 equals pi times 0. So that's why we call it indeterminate. We cannot determine what this number is just by leaving it in the form of 0 over 0. So we need something other than plug and chug on this one. So let's try a different approach. That is reducing this first. X cubed minus 1 over x minus 1. When we put 1 in, we're getting that 0 over 0. If we can factor out the x minus 1, we might be in luck here. And sure enough, when we do some synthetic division on this, that's a negative 1, you get x squared plus x plus 1. And so now, if we look at this sort of g of x squared plus x plus 1, and look at g of 1, you get 1 squared plus 1 plus 1. And that's equal to 3. And so that's what's happening down here on the function x squared plus x plus 3. 1 can actually go in and you get a y coordinate of 3. Whereas on the original function, the f function, if we put 1 in, we got undefined. We got 0 over 0. So some interesting things here. F of 1 is undefined. But now we can use the theorem that was just mentioned on this previous page. That is, if you can get two functions to agree everywhere except at a value of x, then they will have the same limit. So, we can look at this again and say the limit as x approaches 1 of f of x will equal the limit as x approaches 1 of g of x. And that's what I did over here in this page, and we actually came up with the answer of 3. So even though the function's undefined at x equals 1, there is a limit, and the limit is well defined because in both directions we seem to be getting closer and closer and closer to a y value of 3. Now here's some strategies for finding limits. You're going to eventually be able to recognize very quickly when you can just go ahead and use direct substitution. Basically, if you don't get any divisions by 0 over 0 over 0, you're in good shape. Okay? Now, if it can't be, then try and reduce it algebraically. And here, the next few things, there's a bunch of tricks for figuring out how to reduce these algebraically. For instance, on this one here, we've got oopsie, I went too far, sorry. Dividing out technique. Limit as x goes to negative 3 of x squared plus x minus 6 over x plus 3. If we just put a negative 3 in now, we're going to get division by 0. So let's use our synthetic substitution to look at a function very much like this, the reduced function, negative 3, negative 2, 6, 0. And this basically reduces down to x minus 2. So it's a limit as x goes to negative 3 of x minus 2. That's just negative 3 minus 2, which is negative 5. Now, a lot of times this won't actually show up on your calculator. It won't actually show the whole unless you happen to exactly, the calculator actually does x equals 2 for the limit. Now here's the rationalizing technique, probably the trickiest one. If we put 0 in, notice if you just try and plug and chug, PNC, plug and chug, you get square root of 0 plus 1 minus 1 over square root of 0, or sorry, over 0. Still, that's 1 minus 1 over 0, that's 0 over 0, that's the indeterminate form. Go back and try and think of something algebraic. Now this thing does not factor, square root of x plus 1 minus 1. So we do this little trick for the limit as x goes to 0 of the square root of x plus 1 minus 1 over x. We actually multiply it by the conjugate of the top, the square root of x plus 1 plus 1 over the square root of x plus 1 plus 1. I might think, how can that possibly help? You'll see. You'll see. We get the limit then, as x goes to 0, of, when I multiply these two conjugates, I'll end up with the difference of squares. Square root of x plus 1 squared minus 1 squared all over x times all that other junk. Square root of x plus 1 plus 1. On top, we see it simplifying. We get x plus 1, because squaring will undo the square root, minus 1 over x times all that yada yada. And then limit as x goes to 0 of x over x times the square root of x plus 1 plus 1. We're going to need another page yet. Finally, the x's fall out. X over x is 1, so we get 1 all over square root of x plus 1 plus 1. And now when we evaluate this by direct substitution, we get square root of 0 plus 1 plus 1. 1 over 1 plus 1 is a half. So there's your limit. You can check this on your T89. We talked about this before. Let's take a look at that. Checking with the TI89. Okay, on the TI89, what you enter is limit of left parentheses square root of left parentheses x plus 1, right parentheses minus 1, right parentheses divided by x. That's just getting in the function we're trying to take the limit of. You got to tell it the variable, that's the independent variable x, and then you have to tell it the value that x is approaching, 0. And it does come up with exactly a half. Now, please don't abuse this power of your calculator, because on the test you will be expected to do this by hand. It's certainly something you can use to check while you're working your WebAssign and checking on the test, so you know if you got the right answer or not. But you're going to have to show me this technique when you're simplifying a limit. Finally, we're going to look at something called the squeeze theorem, which is this idea that if one function can get in between another two functions, then if the two functions that are bounding it approach the same limit, that squeezed function will also approach that limit. And I want to illustrate this with GeoGebra. Okay, here's the point f, which is on function f. And notice what I've done here is demonstrating that it's always in between the points g and h on the functions g and h, that f of x is always between h of x and g of x. And that's what that vertical line is doing there. So all those points have the same in common, but now watch what happens now as we bring in f closer and closer to 0, as x becomes closer and closer to 0. See how over here we've got f, and here's the g point, and here's the h point. And clearly 0.92 is between 1.298 and 0.769, whatever. Now as we move the f point closer and closer in, the gap between the two points gets narrower, and f is being squeezed in between those two values. Now we're getting very close, and as x gets closer and closer to 0, suddenly it jumps to undefined. But you can zoom in and get more accuracy here. So technically, the sine x over x is undefined at x equals 0, and so is the secant. Actually, the secant and cosine are both defined at 1. The reason it's showing those other points as undefined is because they're based on a line that goes through this function here, the f function. And since that gets undefined, the line disappears. So that's what's meant in the little codicil there, that you don't necessarily have to have the functions defined right at c. Because in this case, sine x over x is definitely not defined at x equals 0. But clearly we can see the limit is getting closer and closer and closer and closer to 1. Okay, that's a squeeze theorem. Let's get back to our notes. And here's some of the results. And I pulled up a table from GeoGebra here so you can see that as we get close, x is closer to 0. I did a little zooming in. The y's are getting very close to that. So in conclusion, the limit as x goes to 0 of sine x over x. We can call this equals, we can say this equals 1, because there's three ideas you have to look at in the squeeze theorem. First, sine of x over x was in between two functions. That is, it was above the cosine of x, but below the secant of x, those two functions. Secondly, the limit as x goes to 0 of the cosine of x, just by direct substitution, is cosine of 0, which equals 1. And we'll review that trig in a bit. The limit as x goes to 0 of the secant of x is the secant of 0, which is also 1. So these three ideas have to come together for this proof of why the limit as x goes 0 of sine of x over x equals 1. Okay? That's the squeeze theorem. Flange. Okay. I need a haircut.